Picture this. You wake up and it's raining. Next week, it will still rain. Next month, it will still rain. Next year, it will still rain. Now keep that going for 2 million years. No joke, no exaggeration. Just rain, rain, and more rain until the entire planet turns into one giant swamp and the rulebook of evolution gets shredded. This actually happened. Around 234 million years ago, Earth's weather broke in the weirdest possible way, flooding deserts, drowning ecosystems, and accidentally handing the keys to the planet over to dinosaurs. Scientists call it the Carnian Pluvial episode, which is a fancy way of saying that time it rained for so long that we're still confused about how anything survived. What caused it? Why didn't it stop? And how did a 2 million year thunderstorm accidentally create the age of dinosaurs? Let's find out. When Pangaea was one giant oven. Before the rain came and broke everything, the world looked like someone had taken all the continents, smashed them into one massive landmass, and cranked the thermostat up to desert everywhere. This was Pangaea, the supercontinent, and it was brutal. We're talking about 237 million years ago, in the middle of the Triassic period, when life was still crawling back from the worst extinction event in history. The Permian-Triassic wipeout that had killed over 90% of everything in the oceans and most things on land. Imagine trying to walk from the coast to the centre of Pangaea. You start at the beach, where it's hot but bearable. Rivers cut through the landscape. There's some green. Then you keep walking inland, and it just gets worse. Hotter, drier. The rivers disappear. Plants become scarce. Eventually, you hit the interior, and it's just endless desert. Red sand, baked rock, and absolutely nothing alive except maybe some desperate reptiles hiding under rocks during the day. The coasts were the only places that didn't completely suck. River deltas, shallow seas, forests clinging to valleys where water still flowed. That's where most life is concentrated. Reptiles were running the show. Early relatives of crocodiles, weird-beaked herbivores, big predatory things that looked like dinosaurs but weren't. Actual dinosaurs existed at this point, but they were small, rare, and stuck in the corners of South America and Africa. Nobody was paying attention to them. Plants were limited. Conifers, seed ferns, cycads, basically tough, hardy stuff that could handle seasonal droughts. No flowers yet. No grass. The forests that did exist were patchy and restricted to areas with reliable water. Most of Pangaea was brown, red or grey. If you could see the planet from space, it would look like Mars with oceans around the edges. The climate was seasonal but predictable. Monsoons in some coastal areas, dry seasons everywhere else. Carbon dioxide levels were higher than today, keeping global temperatures warm. But the key thing is, the climate made sense. Animals and plants could adapt to the cycles. Rivers flooded, then dried up. Rain came, then stopped. Life figured it out. Then something broke. Geologists drilling into rocks from this time see it clearly. Layers of red desert sandstone, evaporites, dry as bone sediments. And then suddenly, without warning, the rocks turned dark. Mudstones, shales, coal, wet signatures. The kind of rocks that say, this place was underwater or close to it. And this shift happens everywhere. Europe, North America, China, South America. Not gradually, fast, geologically fast, which means over maybe a few 100,000 years instead of tens of millions. The Carnian stage of the Triassic, which had been cruising along as a hot, mostly dry world, suddenly flipped into something nobody expected. The deserts started flooding. Lakes that had been dry for millions of years filled up. Rivers that had been seasonal trickles turned into permanent, raging torrents. And the rain just didn't stop. The rocks scream. Something went very wrong. Here's how we know this actually happened and isn't just some made-up story. The rocks. Rocks are basically Earth's hard drive. recording everything that happened when they formed. And when geologists crack open Carnian-aged rocks from around the world, they all tell the same weird story. Take the Dolomites in northern Italy. Gorgeous mountains, popular with hikers, and also one of the best places to read Carnian rocks. Below a certain layer, you've got limestone, nice, clean, shallow water limestone that formed in warm, clear seas. These are the kind of rocks you get when life is chill, reefs are building, and everything's stable. Then suddenly that limestone stops. What replaces it? Mud. Tons and tons of mud, silt and clay. Terrigenous sediment, meaning it came from land, washed into the sea by rivers. The water went from crystal clear to chocolate brown in geological terms. That mud layer is thick, sometimes tens of meters, and it's full of organic material. Plant debris, carbon-rich gunk, the kind of stuff that piles up when forests are growing like crazy and rivers are dumping everything into the ocean. Above the mud, limestone comes back, but it's different. The ecosystems had changed. The reefs that had been there before were gone, replaced by simpler, less diverse communities. This same pattern shows up in Central Europe, in ancient lake beds. Lakes that had been shallow, sometimes dry, suddenly got deep and stayed deep. The pollen record, microscopic plant pollen preserved in the sediment, shifts dramatically. Pollen from dry-loving plants drops off a cliff. Pollen from ferns and moisture-loving conifers explodes. The vegetation flipped from desert scrub to forest almost overnight. Then there's coal. Coal is the ultimate smoking gun for, it was really, really wet here. You don't get coal in deserts. You get coal in swamps, where plants grow thick and fast, get waterlogged and pile up faster than they can rot. During the Carnian Pluvial episode, coal seams appear in places that hadn't seen coal formation in tens of millions of years. In parts of China, Europe, and North America, thick coal layers marked this exact interval. These weren't small patches of swamp. These were vast, continent-spanning wetlands. Ocean cores tell the same story from a different angle. In the Tethys Sea, the big ocean that cut into the eastern side of Pangaea, sediment cores show a sudden spike in clay minerals and organic carbon washing in from land. Normally, tropical seas are nutrient-poor and clear, dominated by carbonate production. But during the Carnian Pluvial episode, rivers were dumping so much sediment and organic matter that carbonate production crashed, reefs got buried, ocean chemistry went haywire. Then you get into isotope geochemistry, which is where things get really precise. Scientists measure ratios of carbon isotopes in ancient rocks. During the Carnian Pluvial episode, carbon isotope ratios show a negative excursion, a shift that indicates a massive input of organic carbon into the system. This happens when you're burying a ton of plant material and when forests are pulling CO2 out of the atmosphere faster than usual. Oxygen isotopes shift too, consistent with increased freshwater input and changes in temperature. The craziest part? This all happened fast. Not overnight fast, but fast for geology. The transition from dry to wet conditions took maybe a few 100,000 years. For context, the entire history of modern humans is only about 300,000 years. The Carnian flip happened in about that time, which in Earth's timeline is like snapping your fingers. And it wasn't one smooth, continuous rainstorm. The rocks show multiple pulses, intense wet periods separated by brief, drier intervals. Like the climate was stuttering, trying to stabilize but getting slammed with another wave of rain every few 100,000 years. Over and over, for roughly 2 million years. Fossils in these wet layer rocks show clear stress signals. Reef organisms decline or vanish. Certain reptile groups that love dry habitats disappear from the fossil record. At the same time, new groups show up. Animals and plants better adapted to forests and wetlands. The Carnian Pluvial episode wasn't just weather. It was a filter, sorting life into winners and losers based on who could handle getting drowned for 2 million years. Volcanoes broke the planet's weather. So what the hell caused 2 million years of non-stop rain? The prime suspect is volcanic activity, so massive it makes modern eruptions look like birthday candles. Specifically, scientists point to the Wrangellia Large igneous province, a volcanic event that erupted along what's now the western coast of North America, British Columbia, Alaska, that whole region. Large igneous provinces, or LIPS, aren't your typical volcanoes. They're not dramatic explosions like Mount St. Helens. They're flood basalts, magma just pouring out of the ground, oozing across the landscape like a slow-motion lava apocalypse. But the volume is insane. We're talking over 1 million cubic kilometres of lava, entire landscapes buried under layer after layer of basalt, sometimes hundreds of metres thick. The Wrangellia Lip erupted right around 234 million years ago, exactly when the Carnian Pluvial episode kicked off. Coincidence? Probably not. These eruptions weren't quick. They lasted for hundreds of thousands of years, steadily pumping out lava and, more importantly, volcanic gases. The key gas is carbon dioxide. When basaltic magma reaches the surface, it releases dissolved CO2. For one volcano, that's not a big deal. For a large igneous province erupting for 500,000 years, it's a climate bomb. Estimates suggest the Wrangellia eruptions dumped enough CO2 into the atmosphere to double or triple pre-existing levels. And CO2 is a greenhouse gas. More CO2 means a warmer planet. But it's not just about getting hotter. Warmer air holds more moisture. Warmer oceans evaporate faster. That extra water vapour gets cycled into the atmosphere, and eventually it has to come down. The Carnian warming supercharged the water cycle. Monsoons that had been seasonal became year-round. Rain belts that had been confined to the coasts pushed inland. The interior of Pangaea, which had been a baking desert, suddenly got drenched by moisture pulled in from the oceans. There's also sulfur dioxide in the mix. Volcanic eruptions release SO2, which forms sulfuric acid aerosols in the atmosphere. These aerosols reflect sunlight, causing short-term cooling. That creates a whiplash effect, warming from CO2, brief cooling from sulfur, then more warming when the sulfur settles out. Some models suggest the Carnian Pluvial episode involved pulses of warming and cooling, which could explain why the rocks show multiple wet intervals instead of one continuous flood. The eruptions might have also triggered feedback loops. More rain means more plant growth. More plants mean more carbon pulled out of the atmosphere and buried in swamps. But more plant growth also means more chemical weathering of rocks, releasing nutrients into rivers that eventually wash into the oceans. Those nutrients fuel algae blooms. Algae die, sink, decay and consume oxygen, creating dead zones. Ocean chemistry shifts, marine life dies, and the carbon cycle gets even more tangled. Recent computer models have tried to simulate the Carnian climate. When researchers plug in CO2 levels consistent with Wrangellia volcanism, the models spit out results that match the geological evidence: intensified monsoons, expanded wetlands, increased river discharge, and shifts in vegetation zones. The models aren't perfect. They struggle with regional details, but they confirm that volcanic CO2 is a plausible, even likely, trigger for what happened. Not everyone is 100% convinced though. Some researchers argue that volcanism alone might not be enough. Maybe there were other factors: changes in ocean circulation, orbital variations, even asteroid impacts. There's evidence for smaller volcanic eruptions in other parts of Pangaea during the Carnian. Maybe it wasn't one giant volcanic event, but a cascade of smaller ones, all piling on at once. What's clear is that something injected a massive amount of greenhouse gas into the atmosphere, fast enough and sustained enough to flip the climate into a mode it hadn't been in before, and wouldn't be in again for millions of years. Rangelia is the best candidate, and unless someone finds a better explanation, it's the volcano that broke Earth's weather for 2 million years. Everything either adapted or died. When the rain started and didn't stop, every living thing on the planet had two choices: figure out how to survive in the new waterlogged nightmare or go extinct. The fossil record shows that a lot of species picked option 2, whether they wanted to or not. On land, the biggest losers were reptiles that had thrived in dry, open environments. Rhynchosaurs, these weird, beaked herbivores that looked like a cross between a pig and a parrot, had been doing great in the early Carnian. They grazed on tough vegetation in semi-arid scrublands, and their fossils are everywhere in rocks from before the Pluvial episode. Then the forests and swamps spread. Their preferred habitats vanished, and rhynchosaurs went into freefall. By the end of the Triassic, they were extinct. Dicynodonts, another group of herbivores with tusks and beaks, also got hammered. These animals had survived the Permian-Triassic extinction, the worst die-off in history, and had been rebuilding during the Triassic. But the Carnian Pluvial episode knocked them down hard. Some species went extinct outright. Others survived but never recovered their former dominance. The wetter world and changing plant life just didn't suit them. Rauisuchians, big, heavily built predators that had been apex hunters, also struggled. These animals were built for open terrain hunting. They were fast in straight-line shines, powerful but not agile in dense vegetation. When forests thickened and the ground turned into waterlogged mush, their hunting strategies stopped working. They didn't go extinct immediately, but their diversity crashed and they were on their way out. Meanwhile, smaller, more flexible reptiles started winning. Early dinosaurs, which had been rare, small, and confined to specific regions, suddenly found themselves in a world where the old guard was weakening. Dinosaurs had upright postures, efficient locomotion, and they were generally more agile than the big, sprawling Rauisuchians. As forests expanded, dinosaurs spread into new areas and started diversifying. They weren't dominant yet, but the Carnian Pluvial episode gave them a foothold they wouldn't give up. Cynodonts, small, warm-blooded or near-warm-blooded mammal ancestors, also thrived. These were omnivorous or insectivorous animals that could exploit dense underbrush and forest floor habitats. The expansion of forests and the explosion of insect populations gave them plenty of food and places to hide. Some cynodont lineages would eventually evolve into true mammals, and the Carnian Pluvial episode accelerated that transition. In the oceans, it was a bloodbath. Shallow marine carbonate platforms, basically ancient reefs, collapsed under the sediment load. Reefs need clear, sunlit water. The influx of mud from flooded rivers smothered them. Reef-building organisms like certain sponges and algae declined sharply. There's a distinct gap in reef formation during the Carnian Pluvial episode, with reefs only coming back after conditions stabilised. Marine reptiles, though, adapted fast. Ichthyosaurs and nothosaurs were already experimenting with fully aquatic lifestyles, and the chaos in the oceans created new opportunities. Some groups diversified during the Carnian, filling niches left empty by the collapse of reef ecosystems. The oceans didn't die, they just reorganised around new rules. Fish populations shifted too. Some species that depended on reefs or specific water chemistry went extinct. Others, generalists, opportunists, exploded in number. Bony fish and early sharks that could adapt to murky water and changing food sources did well. On land, plant life went absolutely nuts. Forests expanded across areas that had been deserted for millions of years. Conifers, seed ferns and ferns colonised every available patch of wet ground. This vegetation boom had cascading effects: more food for herbivores, more shelter for small animals, more oxygen production, and more carbon burial in swamps. Insects loved it. With more plants came more insects, beetles, flies, early versions of groups that are still around today. Insect populations exploded, which in turn supported insectivorous vertebrates like cynodonts and small reptiles. The food web got richer, more layered, more complex. The pattern is clear. Generalists and opportunists survived. Specialists, animals locked into specific habitats or food sources, got wrecked. The Carnian Pluvial episode rewarded flexibility and crushed rigidity. That's evolution in action, brutal and unforgiving. Dinosaurs accidentally got their big break. Ask anyone what ruled the Mesozoic era, and they'll say dinosaurs without hesitation. But here's the thing. For most of the Triassic, dinosaurs were nobody. They were small, rare, and completely overshadowed by other reptile groups. The Carnian Pluvial episode changed that, not by making dinosaurs instantly dominant, but by cracking open the door that would eventually let them take over. Before the Carnian, dinosaurs were mostly confined to South America and parts of Africa. They were bipedal, small to medium-sized, and occupied marginal ecological niches. The real rulers of the land were Rauisuchians, Aetosaurs and other archosaur groups that had successfully adapted to the hot, dry Triassic climate. Dinosaurs existed, but they were bit players in a world run by others. Then 2 million years of rain happened and everything changed. The reptile groups that had dominated dry, open environments suddenly found themselves in a world of dense forests and waterlogged ground. Rauisuchians, which relied on speed and power in open terrain, struggled in cluttered, muddy environments. Aetosaurs, heavily armoured herbivores that grazed in semi-arid areas, lost their habitats as those areas turned into swamps. Dinosaurs, on the other hand, had advantages that suddenly mattered. Their upright posture, legs positioned directly under the body, made them more efficient movers than sprawling reptiles. In forests and uneven terrain, that efficiency was crucial. Early theropods could dart through underbrush, chase prey into tight spaces, and exploit resources that larger, slower predators couldn't reach. Early sauropodomorphs, ancestors of the giant, long-necked dinosaurs, also benefited. They were still relatively small, but they were starting to experiment with browsing on higher vegetation. As forests expanded and plant diversity increased, sauropodomorphs had more food and more places to live. Reproduction might have played a role too. Many dominant Triassic reptiles laid eggs in specific nesting sites, seasonal floodplains, dry riverbeds. When those areas flooded constantly, nesting success collapsed. Dinosaurs, which may have had more flexible nesting strategies, suffered less reproductive disruption. Over time, that demographic edge compounded. The fossil record shows the shift clearly. In rock layers just after the main Carnian wet pulses, dinosaur fossils become more common. New species start appearing. By the late Triassic, dinosaurs were widespread across Pangaea, occupying a range of niches. They still weren't the only game in town, but they were no longer marginal. The Carnian Pluvial episode also broke down geographic barriers. Before the rains, dinosaur populations were isolated in southern continents. As climate patterns shifted and habitats changed, those barriers weakened. Dinosaurs spread into North America, Europe, and Asia. Once they got footholds in those regions, they diversified rapidly. Some paleontologists argue that the Carnian Pluvial episode was the single most important event in dinosaur evolution. Without it, dinosaurs might have remained minor players, confined to South America and eventually replaced by other groups. The climate chaos didn't create dinosaurs, they already existed, but it gave them the opportunity they needed. The old guard weakened, new habitats opened up, and dinosaurs walked through the door. It wasn't a smooth, instant rise. There were setbacks, local extinctions and continued competition. But the trajectory was set. By the end of the Triassic, dinosaurs were poised to dominate, and a later extinction event at the Triassic-Jurassic boundary would finish the job, removing the last major competitors and leaving dinosaurs as the unchallenged rulers of the land for the next 135 million years. All because it rained for 2 million years and accidentally gave dinosaurs their shot. The oceans drowned in mud. The land got soaked, but the oceans got buried. The Carnian Pluvial episode didn't just flood continents, it wrecked the shallow seas that had been slowly recovering since the Permian extinction. Reefs collapsed, marine ecosystems reorganised, and ocean chemistry went completely sideways. Before the Carnian, shallow tropical seas were starting to look healthy again. Carbonate platforms, underwater limestone shelves built by reefs, were forming. These weren't modern coral reefs. They were built by calcareous sponges, algae, and early corals. The reefs provided structure and habitat for fish, invertebrates, and marine reptiles. Biodiversity was increasing. The oceans were healing. Then the rivers started dumping mud, lots of it. As rainfall intensified on land, erosion rates skyrocketed. Rivers that had been clear turned into brown sludge torrents, carrying tons of silt, clay, and organic debris. When that sediment reached the coasts, it poured into the shallow seas, turning crystal clear water into murky soup. Reefs can't survive that. They need sunlight. The photosynthetic organisms living in them can't function in murky water. Buried under layers of sediment, the reefs suffocated. Geologists studying Carnian marine rocks see this written clearly. Carbonate deposits abruptly give way to thick layers of terrigenous mud. The transition is sharp, happening over just a few metres of rock. The collapse wasn't total. Some reef organisms survived in deeper waters or regions with less river input. But the widespread shallow water reef systems that had characterised the mid-Carnian essentially vanished. This had ripple effects through the entire marine food web. Animals that depended on reefs for food or shelter either went extinct or had to adapt to new environments. Ammonites, coiled shell relatives of modern squid, also took a hit. These were diverse and abundant in Triassic oceans, and paleontologists use their fossils to date rocks. During the Carnian Pluvial episode, several ammonite families went extinct, and overall diversity dropped. The exact cause is debated, but the timing matches the reef collapse and sediment influx. Ocean chemistry itself likely shifted. Increased river runoff brought not just sediment but nutrients: nitrogen, phosphorus, iron. In moderate amounts, nutrients boost productivity. In excess, they cause problems. Algae blooms explode, dianae sink and decay, consuming oxygen. The result is hypoxia or anoxia, low or no oxygen in the water, which kills fish and bottom-dwelling organisms. Evidence for low oxygen conditions shows up in black shales and fossil death layers in some marine sections. Carbon isotope records show the same negative excursion seen in terrestrial rocks, indicating massive organic carbon influx into the oceans. Temperature changes compounded the problem. Warmer water holds less dissolved oxygen. Despite the chaos, some marine groups thrived. Ichthyosaurs diversified during the Carnian. They were fast, open-water hunters, less dependent on reefs. Nothosaurs adapted too. Early sharks and bony fish exploited the disrupted ecosystems, expanding into niches left empty by extinct groups. The marine extinction associated with the Carnian Pluvial episode, sometimes called the Carnian crisis, wasn't one of the big five mass extinctions, but it was significant. Estimates suggest 30 to 40% of marine genera went extinct, concentrated in reef-associated and shallow water groups. Recovery took millions of years. When the oceans did bounce back, they were different. The ecosystems that emerged were more dominated by mobile predators and less reliant on fixed reef structures, a trend that continued into the Jurassic. The Carnian reset button cleared out old forms and made room for new experiments. The carbon cycle lost its mind. Climate doesn't operate in isolation. When volcanic CO2 kicked off the Carnian Pluvial episode, it triggered a cascade of feedback loops that amplified, dampened, and tangled the system into knots. Understanding these feedbacks is key to understanding why the rain lasted so damn long. Carbon isotopes tell the story. Carbon has two stable isotopes, carbon-12 and carbon-13. Plants preferentially take up carbon-12 during photosynthesis. So when you bury a ton of plant material, you remove carbon-12 from the atmosphere, leaving the remaining carbon enriched in carbon-13. Scientists measure these ratios in ancient rocks. During the Carnian Pluvial episode, carbon isotope ratios show a distinct negative excursion, a shift toward lighter values. This indicates a massive input of organic carbon, likely from increased plant growth and burial. As forests exploded and swamps formed, more CO2 was pulled out of the atmosphere and locked in peat and coal. That should have cooled the climate, but volcanic CO2 input was so large and sustained that it overwhelmed this negative feedback. There were also positive feedbacks, processes that amplified change. Warmer temperatures increase chemical weathering of rocks, releasing nutrients into rivers. Those nutrients fertilize ocean algae, which grow, die, sink and release CO2 back into the system. Warming causes weathering. Weathering causes blooms. Blooms cause anoxia and CO2 release. CO2 causes more warming. Breaking out of that loop requires a major system shift. Oxygen isotopes add another layer. The ratio of oxygen 18 to oxygen 16 reflects temperature and water sources. During the Carnian Pluvial episode, oxygen isotope ratios shift in ways consistent with increased freshwater input. Rainwater has a lighter signature than seawater. These shifts are subtle but measurable across multiple sites. Sulfur isotopes offer clues about volcanic activity. When sulfur-rich volcanic gases react with seawater, they alter sulfur isotope ratios. Carnian sulfur isotope anomalies line up with evidence for volcanic pulses, supporting the Wrangellia trigger hypothesis. One tricky aspect is coal formation timing. Normally, coal takes ages to form, but Carnian coal seams suggest rapid, massive burial. This should have acted as a carbon sink, pulling CO2 out. Yet the climate stayed warm and wet, meaning volcanic input was larger than even aggressive carbon burial could compensate for. Climate models try to balance all these factors: volcanic CO2 input, carbon burial, chemical weathering, ocean anoxia, temperature feedbacks, albedo changes. The model suggests the system was in dynamic equilibrium, not stable, but bouncing within a range where wet, warm conditions persisted. There's also the methane wildcard. Methane is a more powerful greenhouse gas than CO2, though it breaks down faster. Some researchers propose that warming and increased wetlands triggered methane release from soils, wetlands, or ocean sediments. If that happened, it would have spiked extreme warming on top of the sea-unaltering O2 baseline. Evidence is indirect. Methane doesn't leave clear isotope signatures, but it's plausible. The Carnian carbon cycle was a mess. Volcanic sources, biological sinks, weathering fluxes, ocean-atmosphere exchanges, and feedback loops all tangled together. The isotope fingerprints in rocks are our best evidence, and research continues refining the picture. Pinning down when the hell this happened. Rocks don't come with timestamps. But geologists have gotten pretty good at figuring out when things happened. For the Carnian Pluvial episode, they've combined multiple dating techniques to build a timeline, roughly 234 to 232 million years ago, lasting 1 to 2 million years. Radiometric dating is the gold standard. Certain volcanic rocks contain minerals like zircon, which trap uranium when they crystallize. Uranium decays into lead at a known rate, so measuring the uranium to lead ratio tells you when the rock formed. Wrangellia basalts have been dated this way, giving ages around 234 to 232 million years, directly tying the eruptions to the climate event. Biostratigraphy uses fossils. Different species evolve and go extinct at different times, so their presence can date rock layers. In the Carnian, ammonites and conodonts are particularly useful. By tracking which species appear and disappear globally, paleontologists subdivide the Carnian into zones. The pluvial episode shows up as a distinct interval marked by specific fossil turnovers. Magnetostratigraphy tracks Earth's magnetic field reversals. The planet's magnetic field flips polarity every few 100,000 to few million years, and rocks record the field direction when they form. By matching reversal patterns to the global magnetic timescale, geologists correlate sections from different continents. Carnian sections show characteristic reversal patterns that anchor the pluvial episode in time. Chemostratigraphy uses chemical signatures like carbon isotope ratios. Because the Carnian Pluvial episode caused a global carbon isotope shift, that shift shows up worldwide at roughly the same time. By identifying the negative excursion, geologists can say, this is the pluvial episode, even where other methods are ambiguous. Combining all these methods gives a consistent picture, started around 234 million years ago with Wrangellia volcanism, lasted 1 to 2 million years with multiple wet pulses, ended around 232 million years ago when volcanic activity declined and feedbacks rebalanced. The duration, 1 to 2 million years, is key. Long enough to fundamentally alter ecosystems and drive evolution, but short enough that rocks preserve a clear before, during, after sequence. It's also short enough that orbital cycles, changes in Earth's orbit affecting climate on tens to hundreds of thousands of year timescales, could have modulated wet pulse intensity. One challenge is that not every rock section has all of the tools. Some have great fossils, but no volcanic layers. Others have volcanic layers, but poor fossils. The best dated sections combine multiple lines of evidence, like marine sections in the Dolomites or terrestrial sections in the Newark supergroup of eastern North America. Despite uncertainties, radiometric dates have error bars of hundreds of thousands of years. The scientific consensus is solid. The Carnian Pluvial episode was real, happened around 234 to 232 million years ago, and lasted roughly 1 to 2 million years. In Earth's timeline, it's a sharp, discrete event, a spike of extreme rainfall sandwiched between more typical Triassic conditions. The rain hit different places differently. The Carnian Pluvial episode was global, but its effects weren't uniform. Some regions got absolutely hammered, while others saw more modest changes. These regional variations depended on geography, ocean proximity, and atmospheric circulation. Equatorial Pangaea, the central belt of the supercontinent, saw the most dramatic changes. Before the pluvial episode, this region was dominated by interior deserts far from oceans. When the rains came, that aridity broke down. Supercharged monsoons pushed moisture deep inland. Rivers that had been dry most of the year became permanent. Seasonal lakes filled and stayed full. Fossil lake deposits show sudden transitions from evaporites and dry lake muds to deep-water sediments and organic layers. Coastal regions, particularly along western Pangaea, modern North America, and eastern Pangaea, modern Europe and Asia, also got drenched. These areas were already wetter, but the pluvial episode amplified precipitation. River systems swelled, deltas expanded, coastal wetlands turned into vast swamps. The Newark supergroup rocks of eastern North America show clear evidence of increased lake levels and expanded vegetation. High-latitude regions, closer to the poles, saw less dramatic changes. Climate was already cooler and wetter there, so more rain didn't flip ecosystems like it did in lower latitudes. Fossil evidence from high-latitude Carnian sites shows continuity rather than disruption, with gradual changes instead of abrupt turnovers. The pluvial episode's effects were strongest in tropics and subtropics, where the shift from dry to wet was most extreme. Mountainous regions provided refugia, areas where local climate buffered broader changes. In highlands, rain shadow effects and elevation gradients created microclimates where conditions remained stable. Some fossil sites show less disruption, and certain organisms that went extinct elsewhere survived in these pockets. After the pluvial episode ended, these refugia likely served as sources for lowland recolonisation. Ocean basins also showed regional differences. The Tethys Sea, cutting into eastern Pangaea, was more directly affected by river runoff than the open Panthalassa Ocean. Tethyan sections show thick terrigenous sediment and clear reef collapses, while open ocean sections show less disruption. Rivers dump sediment into nearby seas, but the vast ocean dilutes local inputs. Marine extinction was more severe in shallow, nearshore environments than in deep ocean. Latitude mattered for ocean chemistry too. Tropical seas, already warm and low in oxygen, became more stressed by nutrients and organic matter from rivers. Temperate and polar seas, cooler and better oxygenated, experienced less severe anokia. Some marine organisms went extinct in tropics, but survived at higher latitudes, only recolonizing tropics after conditions improved. These regional variations are important for understanding life's response. Where change was extreme, extinction rates were high and ecosystems completely restructured. Where change was moderate, ecosystems adapted without collapsing. The global pattern is a mosaic. Some areas devastated, others disrupted, a few nearly untouched. Paleoclimate models simulating the Carnian reproduce many observed patterns. Intense monsoons in the interior, heavy coastal rainfall, less change at high latitudes, regional ocean chemistry differences. Models aren't perfect, but they confirm that the pluvial episode was driven by global forcing, volcanic CO2, with regional responses shaped by geography. When the world turned into a garden. Before the Carnian Pluvial episode, much of Pangaea was brown and barren. Interior deserts, scrubby coasts, forests limited to river valleys. After the rains came, the world turned green. Plant life exploded, transforming landscapes and setting the stage for a richer, more complex biosphere. The pollen record tells the story most clearly. In rock cores from the Carnian, pollen from dry-adapted plants drops off a cliff. Pollen from moisture-loving ferns and conifers explodes. This shift happens fast, geologically speaking, and shows up across multiple continents simultaneously. It's the botanical equivalent of flipping a light switch. Desert plants out, forest plants in. Coal deposits provide the other smoking gun. Coal forms in swamps where plants pile up faster than they can rot. The Carnian Pluvial episode created perfect coal-forming conditions. Constant rain, waterlogged ground, dense vegetation. Coal seams from this time appear in regions that had been dry for millions of years. Some of these coals are thick and widespread, meaning vast wetland systems persisted for hundreds of thousands of years. The plants themselves were mostly conifers, seed ferns and ferns, standard Triassic groups. No flowering plants yet. Conifers adapted quickly to wetter conditions, some developing specialised roots for waterlogged soils. Seed ferns thrived in the new forests. Ferns, which need moisture to complete their life cycles, had a field day. Fern spores dominate some Carnian sediment layers, suggesting thick understory carpets across entire landscapes. The greening had cascading effects. More plants meant more oxygen, more food for herbivores, more shelter. The food web became more complex and productive. Plant roots stabilised soil, reducing erosion. Dense forests slowed water runoff, allowing rain to soak in. Forests increased humidity through transpiration, plants releasing water vapour, which enhanced local rainfall. Once forests were established, they created feedback loops, maintaining wet conditions. Plant diversity also increased. New species of conifers and seed ferns appear in the fossil record during this time. Some may have evolved in response to new ecological opportunities. Others may have been rare species that suddenly became common as conditions shifted in their favour. Large fossil logs in Carnian sediments show growth rings, indicating trees grew for many years before dying. The presence of large trees suggests forests weren't just dense. They were mature, with tall canopies and layered structure. This is a huge change from the scrubby, low vegetation of the early Triassic. The greening wasn't permanent. When the pluvial episode ended and rainfall decreased, some forests retreated. Deserts and semi-arid zones reappeared in Pangaea's interior, though not to the same extent as before. But forests didn't disappear entirely. The pluvial episode had spread plant populations into new regions, and even after it ended, forests persisted where conditions remained favourable. The post-Carnian world was greener than the pre-Carnian world, a lasting legacy of 2 million years of rain. How the storm finally stopped. All storms end. After roughly 2 million years, the Carnian Pluvial episode gradually wound down. But how did it stop? The answer involves the same factors that caused it: volcanism, carbon feedbacks, and Earth's climate machinery slowly grinding back toward equilibrium. The most straightforward explanation: Wrangellia volcanism slowed down and stopped. Large igneous provinces don't erupt forever. They pulse, wax and wane, and eventually run out of magma as the mantle plume weakens or shifts. Once volcanic CO2 flow declined, the greenhouse forcing supercharging the water cycle also declined. Less CO2 meant temperatures dropping and monsoon intensity decreasing. Carbon burial played a supporting role. During the pluvial episode, massive plant burial pulled CO2 out of the atmosphere, locking it as coal. Over hundreds of thousands of years, this carbon sink drew down atmospheric CO2. 2. Gradually weakening the greenhouse effect. The process was slow. Carbon burial doesn't remove CO2 as fast as volcanoes add it, but over time, it made a difference. Chemical weathering also contributed. When rain falls on rocks, it reacts with minerals, breaking them down and consuming CO2. Increased rainfall during the Carnian accelerated weathering, pulling more CO2 out. This is a negative feedback. More rain leads to more weathering, which removes CO2, which reduces greenhouse effect, which reduces rain. Eventually, the system stabilizes at a new equilibrium. Ocean chemistry changes help too. As nutrients washed in and algae blooms consumed them, organic matter was buried in marine sediments, acting as another carbon sink. Once nutrient input declined as rainfall decreased, ocean productivity dropped and carbon burial rates decreased. Orbital forcing might have played a role. Earth's orbit and axial tilt vary on regular cycles, tens to hundreds of thousands of years, affecting solar energy distribution. These cycles can push climate into wetter or drier states. If the Carnian Pluvial episode was amplified by favourable orbital configuration, a shift to less favourable configuration could have helped end it. Some researchers note that wet pulse timing matches known orbital cycle rhythms. The end wasn't a sudden flip. The rock record shows gradual transition. Wet sediments give way to mixed wet and dry deposits, then increasingly dry deposits as typical Triassic conditions return. The climate system didn't snap back, but unwound slowly over hundreds of thousands of years as feedbacks and forcings rebalanced. Regional differences are evident. Some areas stayed wetter longer, others dried faster. This reflects local geography and ocean current influence. Coastal regions saw monsoons weaken gradually, but still experienced more rainfall than interior regions. One question is whether the episode's end triggered its own extinction. When conditions shifted back toward drier climates, species adapted to wet forests and swamps would have been stressed. Some may have gone extinct, others retreated to refugia. The fossil record shows some turnover at the Carnian's end, though less dramatic than at the start. The end was disruptive, but less catastrophic than the beginning. The Carnian Pluvial episode's legacy didn't vanish when rain stopped. The ecosystems that emerged were different from before. Dinosaurs were more widespread and diverse. Mammal ancestors had stronger footholds. Plant communities were more complex. Marine ecosystems had reorganized around new dominant groups. The post-Carnian world was a new world, shaped by 2 million years of rain and the evolutionary responses it provoked. Who made it and who didn't? The Carnian Pluvial episode caused something subtler than a mass extinction, but in some ways more interesting. A selective filter that reshaped life without wiping it out. Some groups went extinct, some declined, but survived. Some thrived. Understanding who made it and who didn't reveals the evolutionary pressures at play. Biggest losers on land. Reptiles adapted to dry, open habitats. Rhynchosaurs went into steep decline and eventual extinction. These herbivores had been incredibly successful, with fossils everywhere across Pangaea. But as forests spread and wetlands expanded, their scrubland habitats vanished. Without the right plants and terrain, rhynchosaurs couldn't compete. By the end of the Triassic, they were gone. Dicynodonts also suffered. These tusked herbivores had been diverse after the Permian-Triassic extinction, but the Carnian hit them hard. Several families went extinct during or after the episode. Survivors were smaller, less diverse, restricted to specific regions. Changes in vegetation and competition from other herbivores, including early dinosaurs, likely sealed their fate. Rauisuchians declined too. These large predatory reptiles had been apex hunters, but dense forests and waterlogged ground made their hunting strategies less effective. They didn't go extinct immediately, but their diversity dropped, and by the late Triassic, emerging theropod dinosaurs overshadowed them. The Carnian weakened their dominance and set them up for eventual replacement. Winners included early dinosaurs, which expanded range and diversity. Cynodons also thrived. These small, agile mammal ancestors were well suited to dense underbrush and complex habitats created by expanding forests. They diversified during the Carnian, and some lineages would give rise to true mammals by the late Triassic or early Jurassic. Pterosaurs, flying reptiles, appear in the fossil record around the Carnian Pluvial episode. Whether the episode directly influenced their origin is unclear, but timing is suggestive. Expanded forests and increased insect diversity created new canopy and aerial niches. Pterosaurs, with powered flight, could exploit those niches uniquely. Their late Triassic success might owe something to pluvial episode ecological opportunities. In oceans, reef-associated organisms were hardest hit. Certain sponges, algae and early corals building Triassic reefs went extinct or became rarer. reef ecosystem collapse reduced habitat and food for many marine species. Ammonites also declined, though some families survived and later recovered. Marine reptiles like ichthyosaurs and nothosaurs adapted and diversified. These groups weren't tied to reefs. They hunted in open water or along coastlines. Ecosystem disruption created opportunities for generalist predators that could adapt. Ichthyosaurs became highly successful in the Jurassic, suggesting the Carnian was a stepping stone rather than a barrier. Fish populations show selective survival. Some groups declined or went extinct, particularly reef-associated specialists. Others expanded, taking advantage of increased nutrient flow and disrupted food webs. Adaptable, generalist bony fish and early sharks did better than specialists. Insects seem to have diversified. Forest expansion created new habitats and food sources. Beetles, flies, and plant-feeding insects all show increased late Triassic diversity, suggesting the pluvial episode boosted insect evolution. The pattern is clear. Generalists and opportunists did better than specialists. Species that could adapt to changing conditions, shift diets, or move into new habitats survived. Species locked into specific niches, certain plants to eat, specific hunting strategies, reef habitat dependence, were more vulnerable. The Carnian rewarded flexibility and punished rigidity. This selective filter had long-term consequences. Groups that survived and thrived became founders of late Triassic and Jurassic ecosystems. Dinosaurs, pterosaurs, mammal ancestors, and adaptable marine reptiles all trace their success partly to having made it through the Pluvial episode. Groups that failed to adapt faded into extinction, leaving only fossils. Other times. Earth's weather broke. The Carnian Pluvial episode wasn't the only time Earth's climate went haywire with extreme rainfall, but it's one of the longest and best documented. Comparing it to other ancient hyper-rain events helps understand what triggers these episodes and their long-term effects. One comparable event is the Paleocene-Eocene thermal maximum, PETM, around 56 million years ago. Rapid global warming, likely from volcanic activity or methane release, spiked temperatures 5 to 8 degrees Celsius in just thousands of years. The PETM didn't produce 2 million years of rain, but it intensified the water cycle, causing extreme precipitation in some regions, droughts in others. Like the Carnian, the PETM reorganized ecosystems, drove some extinctions, and accelerated diversification in others, notably mammals. Another parallel is the Toarcian oceanic anoxic event in the early Jurassic, about 183 million years ago. Karoo-Ferrar large igneous province eruptions pumped CO2 into the atmosphere, warming the planet and disrupting ocean chemistry. Increased rainfall and runoff contributed to ocean anoxia, killing marine life and leaving organic-rich black shales. The Toarcian was shorter, hundreds of thousands rather than millions of years. But mechanisms were similar: volcanism, greenhouse warming, intensified hydrological cycle, widespread ecological disruption. Further back, the Permian-Triassic boundary saw climate chaos, though extreme heat and aridity dominated rather than prolonged rain. However, in the immediate aftermath, there's evidence for intense, localized rainfall events and rapid erosion. These weren't sustained over millions of years, but they hint at climate system instability when pushed to extremes. In the deeper past, the Carboniferous period experienced long intervals of wet, humid conditions. These weren't triggered by single volcanic events, but by combinations: low-latitude continents, extensive shallow seas, high atmospheric oxygen. The Carboniferous wasn't a pluvial episode like the Carnian, but shows prolonged wet conditions can persist when the right factors align. Comparing these events reveals common themes. Volcanism and greenhouse gas release frequently trigger them. Intensified rainfall and runoff disrupt terrestrial and marine ecosystems. Carbon cycle feedbacks crucially amplify and eventually end events. And in every case, life doesn't just passively suffer, it adapts, evolves, and reorganizes. The Carnian stands out because of duration. 2 million years is long enough for evolution to produce new species, for ecosystems to completely reorganize, for effects to cascade through multiple trophic levels. Shorter events like the PETM or Torsian caused major disruptions, but didn't last long enough for the same evolutionary depth. The Carnian, by lasting so long, gave lifetime to adapt in place rather than just survive and wait. These parallels have implications for understanding modern and future climate change. The Carnian shows what happens when you push Earth's climate far out of equilibrium. Ecosystems collapse and reorganize. Species go extinct. The planet takes millions of years to restabilize. The triggers, volcanic CO2 in the past, anthropogenic CO2 today, differ in source but are similar in effect. While we're not looking at 2 million years of future rain, the lesson is clear. Rapid, large-scale climate changes have profound, long-lasting consequences. Computer simulations, trying to recreate the impossible. Scientists can't go back and watch the Carnian Pluvial episode happen, so they use climate models, computer simulations of Earth's atmosphere, oceans, and surface, to recreate ancient conditions and test hypotheses. These models aren't perfect, but they're powerful tools. Modelling the Carnian starts with reconstructing Pangaea's geography. Researchers use paleomagnetic data and geological evidence to map where continents, oceans, and mountain ranges were. They configure the model's virtual planet to match that geography, then add factors like solar radiation, orbital parameters, and atmospheric composition. The key variable is CO2. To simulate the Carnian Pluvial episode, researchers increase atmospheric CO2 to levels consistent with large-scale volcanic outgassing, typically 2 to 4 times pre-industrial levels. They also adjust other greenhouse gases like methane if testing those hypotheses. Once set up, they run the model and see what happens. Results are striking. With high CO2, the model produces intensified monsoons, increased global precipitation, and expanded tropical wet zones. Moisture penetrates deep into Pangaea's interior. Areas that were deserts in low CO2 runs turn green. River discharge increases dramatically. The model reproduces many geological record features: wet pulses, vegetation zone shifts, increased coastal sedimentation. Models also show rainfall distribution wasn't uniform. Equatorial and coastal regions see the most dramatic increases, while high-latitude regions see smaller changes. This matches geological evidence for regional variations. Models suggest the Carnian climate featured strong seasonal monsoons, intense rainfall periods followed by slightly drier intervals, rather than constant, uniform rain everywhere. That fits evidence for multiple wet pulses rather than one continuous deluge. One limitation is resolution. Climate models divide Earth's surface into grids, each cell representing large areas, sometimes hundreds of kilometres per side. Small-scale features like individual mountain ranges or local weather patterns can't be fully captured. Higher resolution models are in development, but require enormous computing power. Another challenge is incorporating feedback. Models can simulate basic atmosphere and ocean physics, but biological feedback, vegetation cover changes, carbon burial, ocean productivity, are harder to include. Earth system models try incorporating these with modules for vegetation dynamics and biogeochemical cycles. When added, models show feedback amplifying volcanic EO2 effects, making wet conditions more intense and longer lasting. Models also test alternative hypotheses. Some researchers proposed ocean circulation changes, rather than volcanic CO2, might have triggered the Carnian Pluvial episode. When modelers test this by altering ocean currents in simulations, circulation changes alone don't produce observed rainfall and sedimentation patterns. CO2 forcing is necessary to match geological evidence. This doesn't rule out ocean circulation roles, but suggests it was secondary rather than primary. Climate models have explored why the episode ended. When researchers gradually reduce CO2 in simulations, the climate system responds by decreasing precipitation and shrinking wet zones. But the transition isn't instant. It takes tens to hundreds of thousands of simulated years for the climate to fully adjust. That matches gradual transitions in the rock record. One exciting development is paleoclimate data assimilation, where models are constrained by actual geological data. Instead of running models with fixed CO2 and seeing what happens, researchers feed in rock information, temperature proxies, vegetation data, ocean chemistry, and adjust models to match observations. This produces more accurate simulations and helps identify which factors were most important. Despite their power, models are still simplifications. They can't capture every ancient world detail, and there are always uncertainties in input data: CO2 levels, solar radiation, topography. But they're improving rapidly, and each new generation gets closer to reproducing Earth's complex climate dynamics. For the Carnian, models have been crucial in confirming volcanic CO2 was the likely trigger, and showing how that cascaded through the climate system to produce 2 million years of rain. What it means for us today. The Carnian Pluvial episode happened 230 million years ago, but it's not just ancient history. It holds lessons for understanding how Earth's climate responds to rapid greenhouse gas increases, a situation we're creating today with fossil fuel emissions. While specifics differ, underlying physics and feedback are the same. The most obvious parallel is CO2. The Carnian was triggered by volcanic CO2 release on a massive scale. Today, humans release CO2 at rates comparable to, and sometimes exceeding, volcanic emissions from large igneous provinces. We're not at Carnian CO2 levels yet, but we're heading that direction if emissions continue unchecked. The Carnian shows what happens when you push CO2 high enough. The climate system responds with warming, intensified rainfall in some regions, and disrupted ecosystems. One key lesson is feedback. In the Carnian, volcanic CO2 triggered warming, which intensified the water cycle, which increased weathering and carbon burial, which eventually drew CO2 back down. But that process took millions of years. The system didn't snap back to normal quickly. It took a long time for feedback to rebalance. That's sobering for today. Even if we stop emitting CO2, the climate system will take centuries to millennia to fully adjust. Some changes, like sea level rise from melting ice sheets, are effectively irreversible on human timescales. The Carnian also demonstrates tipping points. Climate systems don't always respond linearly. Sometimes you push a little and nothing much happens. Then you push a bit more, and suddenly the system flips into a new state, like sudden intensified monsoons in the Carnian. Once flipped, it can be hard to flip back. That's a concern for modern climate change. We might not see full consequences until we've pushed the system past a critical threshold. Regional differences in the Carnian offer another lesson. The episode didn't produce uniform changes. Some regions got drenched, others stayed relatively dry. Today's climate models predict similar regional variations. More rainfall in some areas, droughts in others. Complex, non-uniform weather pattern changes. The Carnian reminds us that global climate change doesn't mean every place experiences the same thing. The biological response is instructive too. Life adapted, evolved, and reorganized, but not without costs. Species went extinct, ecosystems collapsed, and it took millions of years for new, stable ecosystems to emerge. That's the timescale of evolutionary response, far too slow to help species cope with rapid changes we're imposing today. The Carnian shows that while life as a whole survives climate upheaval, individual species and ecosystems often don't. In the modern world, where human societies depend on stable ecosystems and predictable climate, that's critical. There's also a lesson about changing pace. The Carnian unfolded over 1 to 2 million years. Even the rapid onset phase took hundreds of thousands of years. That's fast geologically, but still slow enough that some organisms could migrate, adapt, or find refugia. Today, we're changing the climate on timescales of decades to centuries, orders of magnitude faster. That leaves less adaptation time and increases widespread extinction risk. The Carnian highlights carbon sink rolls. During the episode, carbon burial in swamps and increased weathering helped draw down CO2 and eventually end it. Today, we're doing the opposite, releasing carbon that had been buried for millions of years. Natural carbon sinks. Forests, oceans, soils absorb some emissions, but not all. Understanding how those sinks responded in the past helps predict how they'll respond in the future. Finally, the Carnian is a reminder that Earth's climate has a wide range of possible states. The idea of normal climate is, in some sense, an illusion. Climate is always changing, driven by different forces at different times. The Carnian was one extreme, 2 million years of rain. The Permian-Triassic boundary was another, extreme heat and aridity. The question for today isn't whether the climate will change, it always does. But how fast, how far, and whether human societies can adapt. The Carnian tells us when you push the system hard enough, it responds in dramatic, long-lasting ways. That's a lesson worth remembering. Everything we still don't know. Despite decades of research, the Carnian Pluvial episode still holds mysteries. Scientists have built a solid framework, but details are fuzzy, and fundamental questions remain unanswered. These gaps drive ongoing research and keep the Carnian an active study area. One big question is the exact duration. Was it 1 million years, 2 million, or somewhere between? Different studies using different methods give slightly different answers. Uncertainty comes from radiometric dating limitations. Error bars of hundreds of thousands of years are common, and difficulties correlating rock sections across continents. Tightening the timeline would help constrain climate change, extinction, and evolutionary response rates. Another mystery is detailed wet pulse structure. The rock record shows the Carnian wasn't one continuous rainstorm, but pulses separated by drier intervals. But how many pulses? How long did each last? What caused oscillations? Some researchers suggest orbital forcing, orbit and tilt changes modulating climate on predictable cycles. Others think volcanic activity itself was pulsed, with eruption bursts followed by quiet periods. Evidence is ambiguous. More high-resolution studies are needed. Methane's role is also unclear. Some researchers say propose methane release amplified warming and rainfall. Methane can come from wetlands, thawing permafrost, or destabilized ocean sediments. If Carnian warming triggered massive methane release, it would explain some of the most intense wet pulses. But methane breaks down quickly and doesn't leave clear isotope signatures, so proving this is difficult. New organic geochemistry techniques might eventually provide answers. We also don't fully understand why the Carnian lasted so much longer than other similar events. The PETM lasted only around 200,000 years. despite also involving volcanic CO2 release. Why did the Carnian last 10 times longer? Was volcanic input sustained longer? Were carbon cycle feedbacks different? Did Pangaea's geography play a role in maintaining wet conditions? These questions are still debated. The biological response is another uncertainty area. We know which groups went extinct and which survived, but not always why. What made early dinosaurs so successful? Was it physiology, behaviour, reproduction, or just luck? Why did rhynchosaurs fail while other herbivores adapted? Answering requires detailed fossil anatomy, physiology, and ecology studies, areas where data is often sparse. There's also the question of whether the Carnian Pluvial episode was a single event or multiple overlapping events. Some researchers argue what we call the episode might be 2 or 3 separate climate disruptions, each with its own trigger, each affecting different regions. The rock record is complex. Teasing apart overlapping signals is challenging. More high-resolution stratigraphy and correlation work will help clarify this. Finally, there's the mystery of how life recovered. After the episode ended, ecosystems reorganized, but recovery details are poorly understood. How long did diversity take to rebound? Did recovery happen at the same rate in different regions? What role did refugia play providing source populations for recolonization? These questions apply to any extinction or disruption event, and the Carnian provides a case study informing broader ecosystem resilience and recovery theories. Ongoing research chips away at these questions. New fossil discoveries, improved dating techniques, higher resolution climate models, and innovative geochemical analyses all contribute to deeper understanding. Each new study fills in a puzzle piece, but the picture is incomplete. That's part of what makes paleoclimatology exciting. There's always more to discover, always another mystery to solve. The world that rain built. Step back and look at the big picture, and the Carnian Pluvial episode emerges as one of the most important events in life's history. It wasn't the biggest extinction, wasn't the most extreme climate event, but it was a turning point, a moment when evolution's trajectory shifted in ways still echoing today. Before the Carnian, the Triassic world was dominated by reptile groups that survived the Permian-Triassic extinction. These were inheritors of a devastated planet, rebuilding ecosystems from scratch. They'd filled most available niches, and the world seemed to be settling into new equilibrium. Dinosaurs existed, but they were marginal, confined to corners where they didn't compete directly with dominant groups. The Carnian Pluvial episode broke that equilibrium. 2 million years of rain reshaped landscapes, reorganized ecosystems, and opened new ecological opportunities. Old dominant groups adapted to dry, open environments declined or went extinct. New groups, dinosaurs, mammal ancestors, adaptable marine reptiles, seized opportunities and expanded. When the rain stopped and the world stabilized again, it was a different world with different rulers. That shift set the stage for the Jurassic and Cretaceous, the age of dinosaurs. Without the Carnian, dinosaurs might never have achieved dominance. They might have remained small, rare reptiles, eventually replaced or marginalized. Instead, the episode gave them a foothold, and later events, like the Triassic-Jurassic extinction, solidified their dominance. The Carnian was the first step in a chain leading to T-Rex, Brachiosaurus, and all the iconic dinosaurs we know. The Carnian also influenced mammal evolution. Cynodonts diversified during the episode, adapting to dense forests and complex habitats. Some lineages would give rise to true mammals, which would survive dinosaur extinction and eventually dominate the Cenozoic. The path from synapsid reptiles to modern mammals runs through the Carnian, and evolutionary innovations during that time, jaw mechanics improvements, hearing, metabolism, were crucial to later mammalian success. In the oceans, The Carnian reorganised marine ecosystems in ways persisting into the Jurassic. Triassic reef collapse cleared the way for new reef-building organisms, including scleractinian corals dominating modern reefs. Marine reptile diversification set the stage for rich Jurassic marine ecosystems. The Carnian was a reset button, clearing old forms and making room for new experiments. The episode also left a physical legacy in rocks. Coal seams, terrigenous sediments, isotope excursions, all are records of what happened frozen in stone for geologists to read millions of years later. Those rocks tell a story of a planet pushed to its limits and then slowly recovering, deciphered piece by generations of scientists. But perhaps the most important legacy is what it teaches about life's resilience and fragility. Life survived the episode. It adapted, evolved, and thrived, but it didn't survive unchanged. Species went extinct, ecosystems collapsed, and millions of years were needed for recovery. Life as a whole is resilient, but individual species and ecosystems are fragile. That's a lesson applying not just to the Carnian, but to any time in Earth's history, including today. The Carnian Pluvial episode reminds us that Earth's climate isn't a static backdrop, but an active, dynamic force shaping evolution's course. When climate changes, life changes with it. Sometimes those changes are gradual and manageable. Other times, they're catastrophic and transformative. The Carnian was one of those transformative moments, a 2 million year rainstorm that rewrote life's rules on Earth. And in doing so, it set the stage for the world we know today, a world where dinosaurs once ruled, where mammals eventually rose, and where the past's lessons can help us navigate an uncertain future. If prehistory taught us anything, it's that Earth can get way weirder than any textbook admits. 2 million years of rain, forests drowning deserts, dinosaurs accidentally getting their shot. None of this should be real, but it is. The Carnian Pluvial episode happened, and it changed everything. The atmosphere became a permanent waterfall. Let's talk about what 2 million years of rain actually means for the sky itself. The Carnian atmosphere wasn't just wetter than usual, it became a fundamentally different beast, operating under rules that don't apply to modern weather, with volcanic CO. O2 spiking atmospheric temperatures between 3 and 10 degrees Celsius above an already hot Triassic baseline, the air became a water-absorbing monster. Physics is brutal here. For every degree of warming, the atmosphere can hold about 7% more water vapour. Do that math across 5 to 10 degrees, and you're looking at 50 to 70% more moisture hanging in the air at any given time. That's not a weather pattern. That's a different planet. Modern Earth processes about 500,000 cubic kilometres of water through the atmosphere annually. Evaporation from oceans, precipitation onto land, the whole cycle. Carnian Earth was probably moving double or triple that volume. The sheer amount of water being cycled through the sky every year was insane. Rivers of moisture flowing through the atmosphere, condensing, falling, evaporating, rising and falling again in an endless loop. The mechanics of Carnian rainfall were probably nothing like what we see today. Modern monsoons are seasonal. Temperature differences between land and ocean drive moisture inland during summer. Then the pattern reverses. But in the Carnian, baseline temperatures were so elevated and CO2 forcing so sustained that the monsoon mechanism never really shut off. Instead of seasonal switches, you get year-round moisture transport from ocean to land. Atmospheric rivers, those concentrated bands of water vapour that occasionally slam into coastlines today, were probably permanent features during the Carnian. Instead of transient phenomena that form, dump rain and dissipate, Carnian atmospheric rivers likely persisted for years, decades, maybe centuries. Imagine a fire hose of moisture pointed at the same coastline for 1,000 years straight. That's what parts of Pangaea were dealing with. The interior of Pangaea got hit with a bizarre effect. With increased temperature gradient between the superheated continental core and relatively cooler oceans, wind patterns intensified. Stronger winds mean more efficient moisture transport. Climate models show persistent low-pressure systems forming over the interior. Giant atmospheric vacuum pumps sucking moisture inland. Once there, the air rises, cools, precipitates, and the cycle repeats. An infinite rain machine. Cloud cover would have been near constant. With so much atmospheric moisture, clear skies became rare luxuries. Paleoclimate models show persistent cloud decks extending from coasts deep inland. Those clouds reflected incoming solar radiation, a cooling feedback, but also trapped outgoing heat at night, keeping temperatures elevated. The result? A world where the sky was grey more often than blue, where sunlight was filtered through perpetual cloud layers, where stars were memories. Lightning must have been absolutely constant. More moisture means more convection means more thunderstorms. Some researchers estimate the global lightning strike frequency during the Carnian could have been 5 to 10 times higher than today. The atmosphere was electrically hyperactive, with storms brewing continuously across vast swaths of the planet. The sound of thunder would have been as common as birdsong today. Here's a disturbing detail from the Paleosol record. Ancient soils show extreme weathering patterns consistent not just with lots of rain, but with acidic rain. When you have constant volcanic emissions plus abundant atmospheric moisture, you get sulfuric and carbonic acid formation. Carnian rainwater was probably pH 4 to 5, noticeably acidic. Not instantly corrosive, but over decades and centuries, that acidity strips minerals from rock faster than normal. Plants growing in Carnian soils were dealing with acid rain every single day for 2 million years. The humidity itself would have been oppressive in tropical zones. Modern tropical rainforests hit 90 to 100% relative humidity during rain. Carnian forests probably lived at those levels perpetually. Everything would have been permanently damp: bark, leaves, soil, rocks. Mold and fungal growth must have been explosive. Any organism living on the forest floor was basically living underwater with air mixed in. But here's what really breaks your brain. This wasn't weather in the sense we understand it. Weather implies variation, patterns you can predict, cycles you can adapt to. The Carnian Pluvial episode was just the climate. Imagine being a dinosaur born into that world. You live your entire life, maybe 40, 50 years, and it rains almost every day. Your parents' entire lives, rain. Their parents, rain. Rain isn't an event. It's the default state of reality. The idea of dry season would have been a myth passed down from pre-Carnian ancestors who remembered a world that no longer existed. And the craziest part, for the organisms that evolved during the Carnian, this was normal. They had no frame of reference for anything else. When the episode finally ended and rainfall decreased, it would have been as disruptive to them as the start had been to pre-Carnian species. Evolution had adapted to the rain, built ecosystems around perpetual wetness, and when that disappeared, everything had to adapt all over again. The atmosphere during the Carnian Pluvial episode was a machine specifically designed to move water from ocean to land, dump it, and repeat. For 2 million years, that machine ran at maximum capacity without breaking down. It's one of the most extreme, sustained climate states in Earth's history, and we're still trying to fully comprehend what it must have been like to exist under that permanently weeping sky. The strangest ecosystems that ever existed. When you take normal habitats and drown them for 2 million years, you don't get wet versions of those habitats. you get something entirely new. Ecosystems that operate under rules so weird, they make modern rainforests look boring by comparison. Start with the Carnian swamp forests. These weren't like modern swamps. The Everglades, the Amazon floodplains, the Congo Basin. Those places are wet-hot, sure, but they're embedded in larger landscapes with variation. Dry ground exists nearby. You can walk out of the swamp if you need to. Carnian swamp forests had nowhere to go. The entire continent was swampy. For thousands of kilometres in any direction, just waterlogged forest, standing water and mud. It was swampy all the way down. The plant communities were alien. Modern swamp trees like mangroves and cypress evolved for periodic flooding. Adaptations like prop roots and knees that stick up through water to breathe. Carnian plants didn't need those features because flooding wasn't periodic. It was permanent. Instead, fossil root systems show shallow, spreading mats that maximised oxygen uptake from the soil-water interface. Some show hollow chambers, probably air channels transporting oxygen from leaves to submerged roots. Tree density must have been absolutely bonkers. In normal forests, trees space themselves based on competition for water and nutrients. Water wasn't limited in Carnian forests. Nutrients were being constantly delivered by flooding rivers. The main competition was for light. That means forests probably grew as insanely dense walls of vegetation where every vertical centimetre was occupied. Ferns packed the understory. Conifers and seed ferns battled for canopy space. There was no open ground, just layers upon layers of plants stacked from waterline to sky. The forest floor was basically a drowned nightmare. Not solid ground, but a semi-liquid environment of waterlogged organic matter, fallen logs, standing water, and decomposing plant material. Walking would have been impossible. You couldn't walk through a Carnian forest. You'd wade, swim, or climb. Any animal living at ground level had to be functionally amphibious. Herbivore behaviour would have been surreal. Pre-Carnian herbivores were built for solid ground, walking, running, grazing. During the Carnian, some herbivorous reptiles show evidence of semi-aquatic adaptations in their footprints, deep impressions, belly drag marks, swimming motions. These animals were feeding while partially submerged, wading through chest-deep water to reach vegetation. Some early dinosaurs may have exploited this by being better waders than their competitors. Their bipedal stance and long legs let them access deeper water that bogged down sprawling reptiles. Predator-prey dynamics got completely inverted. In normal terrestrial ecosystems, predators rely on speed, ambush, or endurance. None of those work in waist-deep water and dense vegetation. You can't sprint, you can't hide effectively, you can't chase. So Carnian predators probably shifted to sit-and-wait strategies, lurking near game trails, water crossings, or feeding areas. Some predatory reptiles show adaptation suggesting they hunted from the water, crocodile style, even though they weren't crocodiles. Insect life must have been hellish. Swamps are insect factories. All that standing water creates perfect breeding grounds. Modern wetlands support massive mosquito, fly and beetle populations. Carnian swamps would have been worse. With insect populations exploding, insectivorous animals had unlimited food, but disease vectors would have been intense. While we can't directly detect ancient diseases, some Carnian vertebrate fossils show weird bone pathologies, lesions, abnormal growths, signs of chronic infections. Living in permanently wet, insect-rich environments would have been a disease nightmare. Decomposition barely worked. In normal forests, dead stuff rots quickly thanks to bacteria, fungi and decomposer insects. In waterlogged, low-oxygen Carnian swamps, decomposition slowed to a crawl. Dead trees, fallen logs, animal carcasses accumulated in huge piles. This is exactly how you make coal. Tons of organic matter piling up in anoxic water where it can't fully decay. It also means Carnian forests were littered with slowly rotting debris, creating a landscape that was equal parts living forest and organic graveyard. The swamp water itself would have been nasty, dark, acidic, tannin-stained from all the decaying plant matter. Nutrients were high, but oxygen was low, especially at depth. Fish and aquatic organisms had to deal with daily oxygen swings, higher during the day when plants photosynthesized, dangerously low at night when respiration consumed it. Anything living in Carnian swamp water needed serious physiological adaptations to handle that instability. And the biomass, holy hell, the biomass. With year-round growing seasons in tropical zones, constant water and unlimited nutrients from flooding, plant productivity was off the charts. Estimates based on coal accumulation rates suggest Carnian swamps were producing and burying organic carbon several times faster than modern tropical rainforests. That level of productivity supported absurdly dense animal populations. The sheer amount of living matter per square kilometre would have dwarfed anything we see today. But here's the thing, these ecosystems were fundamentally unstable. They only existed because of the Carnian Pluvial episode's sustained forcing. The moment rainfall decreased, they collapsed. Swamps drained, forests retreated, species adapted to permanent wetness, either went extinct or evolved new adaptations for drier conditions. The Carnian swamp forests were evolutionary experiments that only worked under the most extreme conditions. And when those conditions disappeared, so did the ecosystems. When oceans and continents became one system. Here's something that doesn't get enough attention. The Carnian Pluvial episode created one of the weirdest connections between land and sea in Earth's history. Normally, continents and oceans are separate systems with their own food webs and their own rules. The Carnian broke that separation and forced them to become one tangled, chaotic system. The mechanism was rivers, lots of them, massive ones, all dumping incredible loads of terrestrial material straight into coastal seas. Modern rivers transport about 20 billion tonnes of sediment to oceans annually. Carnian rivers probably moved several times that, concentrated into much shorter coastlines because of Pangaea's geography. The amount of land-derived material flooding into the oceans was staggering. This created brackish coastal zones of insane extent. Normally, brackish water exists in narrow bands around river mouths. During the Carnian, brackish conditions extended kilometres out to sea. Salinity gradients were complex, fresh water on top, salt water below, constant mixing from currents and tides. Marine organisms had to handle wildly variable, unpredictable salinity. Stressful for specialists, but opportunity for generalists. Some marine organisms straight up invaded freshwater. There's fossil evidence of marine fish groups appearing in river deposits during the Carnian. These weren't true freshwater adaptations, more likely marine fish following salinity gradients upstream, exploiting food in brackish zones, and occasionally getting stranded in river channels when they ventured too far. The boundary between marine and freshwater became blurry. The nutrient influx transformed coastal productivity. Tropical oceans are normally nutrient poor, clear blue water because there's not much algae. Carnian rivers pumped nitrogen, phosphorus and iron into coastal zones at unprecedented rates. This fertilized the water, driving massive phytoplankton blooms. Those blooms supported zooplankton, fish, and larger predators. Coastal food webs became insanely productive. But productivity has a dark side. Phytoplankton bloom, die, sink, and decay. Decay consumes oxygen. With sustained nutrient input, coastal waters were locked in a permanent bloom and bust cycle. High productivity alternates with oxygen depletion. This shows up in Carnian marine rocks as alternating layers, organic rich black shale, anoxic conditions, and more oxygenated sediments, productive conditions. The system oscillated between lots of life and dead zone, sometimes on timescales of decades or centuries. Marine reptiles thrived in this chaos. Ichthyosaurs and nothosaurs show up across a huge range of environments: clear marine water, murky coastal zones, brackish river mouths. Their fossils sometimes preserve stomach contents with both marine and terrestrial origin material, suggesting they were opportunistic feeders exploiting the blurred ocean-continent boundary. Some marine reptile fossils have been found far inland in clearly freshwater deposits. Either they got stranded or they were actually living in rivers, which is insane. The sediment load created unique habitats. When rivers dump sediment into the sea, it doesn't settle uniformly. Heavy stuff drops first. Fine stuff settles farther out, creating gradients from coarse sand near shore to fine mud offshore. During the Carnian, these gradients were compressed and exaggerated. Enormous deltas built into shallow seas, creating vast mixed sand-mud substrates unlike anything today. These deltas became biodiversity hotspots: variable substrate, fluctuating salinity, high nutrients, complex structure, perfect conditions for ecological diversification. Some organisms specialized on sandy areas, others on mud, still others on transitions. The result was patchwork ecosystems where diversity was high but unstable. Species compositions changed constantly as river mouths shifted and sediment patterns reorganized. The Carnian demonstrates something crucial about carbon cycling between land and ocean. All that terrestrial organic matter washing into the sea represented a massive carbon flux. Some got respired, releasing CO2. Some got buried in marine sediments, locking carbon away. The balance partly determined atmospheric CO2 levels. Isotope studies suggest that during peak Carnian wet pulses, carbon burial in coastal marine sediments actually exceeded burial in terrestrial swamps. River deltas are incredibly efficient sediment traps. Organic matter gets delivered, settles quickly in low oxygen bottom waters where decomposition is slow, and gets buried under the next sediment load. Carnian coastal zones were functioning as giant carbon burial machines, drawing down atmospheric CO2 faster than terrestrial systems alone. This ocean-continent coupling created a negative feedback that eventually helped end the episode. By burying carbon efficiently, the system drew down CO2 over hundreds of thousands of years, offsetting volcanic input. But here's the paradox. The same rivers supplying sediment for carbon burial were also supplying nutrients, driving productivity, driving anoxia. The system was simultaneously burying carbon, cooling effect, and creating anoxic dead zones, releasing CO2. These competing feedbacks kept the system in a weird dynamic balance. The legacy shows up in fossil patterns. Organisms thriving during the Carnian were those handling variable environments. Generalists, opportunists, species with wide salinity and oxygen tolerances. Specialists requiring stable conditions got wrecked. This selective pressure reshaped marine and terrestrial biotas in lasting ways, favouring ecological flexibility that characterised late Triassic and Jurassic faunas.